All right, so I'm going to try to do another problem here, and here we're going to talk about friction. So friction can be kind of a little bit of an odd thing, but we've got some very straightforward ways of dealing with it. Usually the problem that students have is they see the way it's described in other, in textbooks and such, even in my past notes that you're probably reading, and they get an idea that the equations are telling everything, right? And that's kind of a trend. Is students love to stare at equations, and it's not everything about the problem. And so here's a problem. We're going to push this mop across the floor. It's going to move to the right, so I put in the velocity here. All right, here's our velocity. And we're just outlining what forces. We're told that there's a force. It's through the mop handle, so there's an angle. That makes sense. We're told that there's a mass, and that means there's a weight force downwards, and that makes sense. There's a normal force that's upwards because it's in contact with the floor. And then there's a friction force. We're given this thing. We're like, well, how do we deal with that? It's this thing called the coefficient of kinetic friction. So here's the thing, is that there's some very basic things about friction. Right? One is it tries to prevent the motion of stuff. Obviously, I've done this before and in the video went bad, so I'm doing it again. Friction tries to prevent the motion. So if this thing, if our mop is moving to the right, the frictional force is opposite that. It tries to go to the left. Now, if this wasn't moving, we could predict it's trying to go to the right, and then the frictional force is to the left. All right, we can kind of take judgment of all the other forces and try to figure out where it's going. Well, what are we trying to do with it? But it just tries to prevent the motion. So if you know what the motion is, you know which direction the friction force points. It's opposite. If it's not moving, then the friction force is whatever allows the acceleration to be zero. It balances the free body diagram. What I'm saying is the sum of the forces is zero. So you add up all the other forces and it tells you what the friction force is. If it's just about to move, then there is a maximum force that friction can give, that the surfaces can give to hold the object in place. And that maximum friction force depends on some coefficient times the normal force. Coefficient, when it's just about to move, is called the static coefficient of friction. When it's moving, it's a different coefficient, a kinetic coefficient. And that's what we're given here. We're given this mu sub k is the coefficient of kinetic friction, and it's this particular value. So we want to, I've not drawn a free body diagram here, even though it kind of looks like it. All right, we've put in velocity, and that's a no-no. And we've put in this friction force here that's off from the center. So we're going to draw the free body diagram. And we're going to identify all the forces that could act on the thing. And you're going to go through the list and say, oh, there's a weight by the earth on the mop. I'm being very careful. I'm doing this the way I teach the Radford kids, to label the thing that causes the force, in this case the earth, and the thing that feels the force, the mop. There is a normal force upwards, and it's by the floor on the mop. There is a applied force. So this normal force should be much larger, but there is a applied force by you on the mop. And then there is something to balance out this. There we go. And it is our frictional force. And the friction force has to be caused by the same thing that causes the normal force. So it's the floor on the mop. Now, we'll simplify this down when we write out Newton's second law. But this thing we have to deal with, it has components. And what we're told in the problem is it makes a mop makes an angle, as shown in the diagram, an angle with the floor. So this is our angle theta, if it's not clear in the drawing. This is our angle theta. So there's our sides of the triangle. That implies that there is another force downwards, which is the applied force times sine theta. And then there's the force sliding across the floor, which is F cosine theta. So that's the one that's actually moving the mop. That and the friction force is stopping it. So now we can do Newton's second law. We're going to do the y direction first, and we're going to take up as plus y and across as plus x. So we'll do sum of the forces in the y direction. So in the positive direction, we have the normal force. In the negative direction, we have the weight force plus this sine component of the friction. And since the mop's not plunging through the floor or rising off the floor, this is the mass times acceleration in the x direction, but that equals 0. So what this tells us is that this normal force equals the weight force plus this F sine theta. And so we can write in, that is mass times g plus F sine theta. That's our normal force. Now we do the sum of the forces in the x direction. So this is the one that's going to have the acceleration that's legit, that's actually happening, the acceleration across the floor. So in the positive direction, we have F cosine theta. And in the negative direction, we have the frictional force. And that equals mass times acceleration. This should be in the y direction, not the x. This is the acceleration in the x direction. Now, this is a vector statement. When we start talking about the numbers, what we'll get is F cosine theta minus our frictional force is mass times acceleration. And now we've written out all the equations. This is the 2 bits that we want. We also need to note that this thing is moving. The friction looks like mu sub k times the normal force. So we can plug that in. So I need another sheet of paper here. And what we'll have is, we're going to write everything to solve for the acceleration. So acceleration looks like F cosine theta minus F over the mass, but that equals F cosine theta minus mu sub k times n over the mass, but that equals plugging in this equation up here, F cosine theta minus mu sub k parentheses mg plus F sine theta over the mass. And we can't cancel the mass out everywhere because these function, the applied force doesn't depend on the mass. So we're just going to have to, at this point, plug and chug. So what we have here, go back to our numbers. Our acceleration looks like 41.8 newtons cosine 50.5 degrees minus, and then our 0.350. Then we have our mass, 2.25 kilograms times 9.8 meters per second squared. And we're going to add 41.8 newtons sine 50.5 degrees. And then we're going to divide the whole thing by mass, 2.25 kilograms. So what I'm going to do is in red, I'm going to fill in what these things are. So I'm going to keep track of things here. So I'm trying to save paper. So we have 50.5 cosine times 41.8 is 26.6 newtons. This term is 2.25 times 9.8 is 22.05, and then this term is 41.8 times 50.5 sine 32.2. Did I do this one right? Okay, yeah. So our acceleration looks like this term, and then 0.350, 22.05 newtons plus 32.2 newtons over 2.25 kilograms. And so we just poke this into the thing and try to figure out what it is. So isn't this riveting video? So this whole thing is 18. We're going to add 26.6, and then we're going to divide by 2.25, and we get the acceleration is 20.26 meters per second squared. Now, what you don't know is I have no idea what the correct answer is. And honestly, I kind of don't care. The important thing, the solution, is going from this step, from the free body diagram, and these boxed equations, to this thing. This is the solution. Everything else is algebra. So please note, and I've seen this on a lot of homework, right, is I've seen people jump around on their written work, and they don't show everything, right? Is they certainly, I don't see very many free body diagrams because we haven't, some problems don't need it. But I get to a statement that looks like this. Like that's what I see on some homework. So I'm like, I don't understand what that is. And you're having a hard enough time understanding it, seeing where it came from, seeing that I'm filling in these numbers. And I've got this from this, right? Is the reason we practice being careful on things is because it's important. We're communicating results. And if I can't understand what you're doing, then what can I do? All right. But I want to, if anything, I want to encourage y'all. This is a hard topic. Forces stink because there's no way that I can show you every single possible problem. Right? In kinematics, I can show you a vast majority of the problems. I can show you ballistics, I can show you circular motion, I can show you just any sort of two-dimensional motion. But here, well, I can have lots of different causes of forces, and they can have different functional dependencies. The the technique. You have to draw a free body diagram. You don't have to label it as thoroughly as I've done, but you got to label it so you understand what's going on. You got to have, if there's a weight force, you got to know this is the weight force. If there's friction, you got to know this is the friction. And the other direction's the direction I expect it to move in. You got to have where you find the components. You got to be able to get your angle and get it figured out. How did I know that's the angle? Well, I have to remember back from geometry that if I have two parallel lines, right? So if I have two parallel lines and one crossing, then these angles are equal. And that's what these are. And I have to have that ability to map between imaginary things and real things and be able to say, oh, yeah, that's the angle I want. So it's a hard topic, and I don't expect y'all to get it easily. I don't want you to feel like, I can't do this and everyone else can, because trust me, no one else can. Or the people who are getting it perfect are the ones who have done it all of their lives. I screw up problems. It's okay. I want you to have some confidence here. We're all in the same boat together. So we're going to do another problem. This is a 2-problem video. So it's about 30 minutes long. If you need to pause, pause now. Here's our second problem. This is kind of a weird thing. I don't know if you've all ever one of them things that spin you around really fast and you kind of stick to the wall, and they're because you're going in a circle, you feel gravity out of the circle in a sense. The wall supports you. This is kind of a problem like that. Is how do you actually stay up on the wall, not just fall down? Well, because there's friction. Your feet hold you against the wall so that you don't slide downwards. So there's a block, and you've done some experiments pressing one block against another, and you figure out that if you get it going fast enough, or basically if you have a consistent acceleration, the block doesn't slide. So the information we're given, the mass of the small block, and an acceleration. And then we're asked, well, what's the coefficient of friction between these? So the idea is there's a minimum in here, so we know that we're at the maximum friction force. So you might be looking at us and you're like, well, how the hell do I start on this? Well, you start with the picture, and you've got the picture. You're being accelerated to the right. You've got a block here. And we're going to draw the free body diagram for the block. Okay. Well, here it is. If there were nothing else going on, the way this is drawn, you would expect the block to fall downwards. So there's a weight force. Okay. Clearly, it's not falling down. So that tells you what the friction force is doing. It's holding it up. The friction force is acting here at this surface to hold it upwards. So we'll put in a friction force. And then if there's a friction force, there's a normal force. There's a surface here, and the surface provides a normal force outwards. So there's our normal force. So now we can take this and use it to do Newton's second law. We will take up as positive y, and to the right is positive x. Okay. So we'll sit and say sum of the forces in the x direction. The only force that's in the x direction is our normal force, and that equals the mass times the acceleration in the x direction. We can find that immediately. Our normal force is 0.35 kilograms times 16 meters per second squared. 0.35 times 16 is 5.6 newtons. So now we can do sum of the forces in the y direction. The positive force is the friction. The negative force is the weight. And that equals 0, because from the problem, it is staying still. It's not moving. So our friction force equals the weight force. Okay. So when we have a problem with a friction force and we're told, and we can figure out that it's the maximum friction force, the friction looks like mu times the normal force. So we can start plugging in here. We have the friction force is mu times the normal force, but that equals the mass times g, which is the weight. All right. So this is the important bit. Now we can solve for this coefficient. Mu is mg over n. We know what n is, and we can plug in everything else. It's 0.35 kilograms times 9.8 meters per second squared. Divide by, let me rewrite that again. So over here, mu is mg over n is 0.35 kilograms times 9.8 meters per second squared. Divide by 5.6 newtons. And what we'll get is the units will all cancel. We just get a number, and that's correct for the coefficient. So 0.35 times 9.8 divide by 5.6. Mu is 0.613. There we go. That's, the number is not hugely important, but I tried to do this more like a student would, is when you know you can get a number, calculate it. And, of course you make mistakes and stuff, but the gist, solving the problem was solved when you wrote this boxed equation, this one, and when you drew this diagram. That's the solution. Everything else is putting numbers in to get a final number out of it, because you're trying to actually do something with it. In the real world, you obviously have to calculate numbers, but the physics is in the things that are marked here. So, I hope this was clearer than mud. All right, obviously, if you've got questions, you should ask questions. We're going to do more videos, but they're going to be on circular motion stuff. So I want you to, relax. Things are going to be okay. Watch this, and we will quickly get through this and get to the fun stuff, I think. We'll see how things go.